Hello, everyone. So I'm Julien. I realized, I think Pete said earlier yesterday that the conference started in 2015. I realized I spoke at this conference in 2016, so almost at the beginning. The following year, I was track host. It's a lot of work. I concur. And in 2018, I gave this talk about the deconstructed database and talking about, how we were rebuilding databases and so on. And fast forward to today, I wanted to talk about how the ecosystem matured and how things evolved since that. So, okay, I'm Julien. I'm an officer at the ASF. I also involved with the Technical Advisory Council at the LFAI and Data, the other data foundation. I'll skip the part Pete talked about. And yeah, I was at Yahoo in 2007. So when I'm going to go to the origin of times, this is what I mean, right? Like origin of times of, I guess, the big data ecosystem. Starting with that, and I'll talk about how things have changed in the meantime, right? We were doing a bunch of things, but the technology has evolved quite a bit in the meantime. And I'll talk about how we're going towards composable data systems. So the origin of times. I'm an engineer. Us engineers, we love reinventing the wheel and rebuilding things from first principles, right? If we think about that beginning of Hadoop, there was this idea of we're going to have this abstracted distributed file system, and we have this MapReduce execution engine on top of it, and we're going to be able to do so many things with it. This is the original Hadoop toy that the project is named after. And it comes from this main idea, it's a lot faster to scan data directly closer to the disk than connect over the network, so we are going to move compute to the data. So even though we have this file format, file system abstraction, actually it's not abstracted out to the execution engine, right? It's going to move all the mappers to where the data is, read locally, so it's a lot faster, and then the data gets shuffled over the network, grouped by keys, and then the reducers are going to process it and write locally. So we're kind of optimizing for reading locally, writing locally, moving compute to the data. And it's a great tool for looking for a needle in a haystack, right? Like you can throw a lot of horsepower looking at a lot of things, but it's a very blunt tool, right? So you can look at the haystack for a needle in a haystack with no plows, right? Kind of going through. And it was not unanimous that it was a good thing that we were doing this. If you don't know Michael Stonebreaker, you might know him is, among other things, the inventor of Postgres, like everybody uses today. He's a recipient of the Turing Award that we call the Nobel Prize of Computer Science. So, we owe him a lot of what we've been using today. And so when you talk, so those are his words. So he published this blog post back in the day. So MapReduce, it's a giant step backwards. It's suboptimal optimization. It's not even novel. It's missing all the features we have in databases, and it's incompatible with all the ecosystem that we build around it. Suffice to say, he was not a big fan. Right, and we were like, that's funny. We're doing this MapReduce thing. It's great. We're super happy. What's going on? What did we miss? All right, there's SQL. And SQL's great. It's declarative, right? You kind of say what you want to have as a result, and you don't worry about how it's going to be implemented, right? Like the query engine figures it out. It's a standard, right? Like it works with a lot of things. There are consistency constraints that your data, you can force your data to be a certain shape, and you're going to prevent any bad data to get in there. You know how to evolve schemas. There's lots of semantics around that. There's lots of good things, and it's been there a long time, right? Like SQL was started in the 70s, got standardized in 86, and it's been a lot of iterations since then. So yeah, there's been a lot of work in that domain, and maybe we should take a hint. And so if you think about how this works, where there's this query evaluation, so in SQL, you express your constraints, right? I want data from this table joined with this table. and those are my filters, and SQL figures out a plan, right? So it goes through this step of parsing the query, analyzing what columns come from which table, what do we know about this, optimizes a plan, and find the best way to produce your results. Right, so if we take this example with simple join between two tables, with an aggregate and a function, it goes through these layers, produces a plan where we scan the data on the leaves, and filter, join, group by, produce a result. And so now we have these two things, right? And we need to reconcile, oh, wait a minute, why it's different, why we're using one, why not the others, what's happening. So RDBMSs are fairly complex, right? They're somewhat inflexible, right? They kind of force you to think about everything as to be one schema. We need to figure out if you change the schema, you kind of have to migrate all your data. Data has to be tabular. It's fairly vertically integrated in the sense that the optimizer needs to understand very intimately how the execution works so that it makes the right decision, and everything needs to work well together. Like MapReduce is a lot more simple, and you could say simplistic, right? It's kind of dumb in many ways, but it's very flexible, it's very composable, right? It's just files, so you can try different models, use any format, do various operation, and it's very composable, right? And back in the day, the way we were composing those MapReduce jobs is by stringing them together with XML workflows. So it was not like super ergonomic, but there's lots you could do with this. And you guess what? One thing you can do in particular is implement SQL on top of MapReduce, right? And of course we did, right? You take your query, you parse it, generate a string of MapReduce jobs to execute one after the other, and here you go, right? Like the composable snowplows, it works. And we ended up, a lot of people, were engineers. Oh, I know I could build a database. Look, we can do that. It's just a parser, some logic. We know how to do this. And then we had a whole cottage industry of SQL and Hadoop implementation, various iterations. Some of them have survived to this day, some have not. Right, and if I take the example of Hive, for example, in which we put a bunch of effort, like the first initial release of Hive, parse query, transform into a chain of MapReduce job, results start in Hadoop file system, done. We have something that works, right? However, it works, but to make it efficient and fast and usable for a lot of use cases, there's a lot of work that you actually do, right? Like there's like the first 10% you can do pretty quickly, but actually make a full system, a full database takes a lot of time, right? So you need an actual optimizers that are going to take the best plan, produce the best plan, take advantage of push downs. You need to use vectorization, you need to have a good interchange, you need to use columnar storage to retrieve data efficiently from storage. There's a lot of things to do. Right, and if we go to the next level of details on what those things are, the optimizers have two levels, right? There's you have first level, which is more rule-based, which is the things you always want to do. For example, if you're going to do a join, you want to do the filter before the join, so less data goes over the network, things like that. And things that are less obvious are more cost-based, that depend on context. For example, picking the order of your joins, right? If certain tables are smaller than others, they're going to go in memory. The big tables, you're going to have to stream over them. And if certain joins are more selective than others, you want to do them first, so you have less data for the next one. And so there's lots of things that it depends on context, and we're trying to do statistics about table, how big the table is and things like that, so that we can estimate all those things. Vectorized execution is something that emerged, right? Like it was pioneered in the MonetDB paper, and basically the argument is, if you organize data in columns in memory and you organize your plan in executing column-wise, you're going to take much better advantage of the CPU. And it's kind of not intuitive. It's just like if you think mathematically, a big O notation, whether if I go row-wise or column-wise, I have the same number of operations. However, given how a processor works, it goes a lot faster if you use column-wise. First, processors don't execute instructions one after the other. They start the next instruction before the previous one is finished. That's because processors have an area with a lot of transistors, and to make better use of their transistors, they split those instructions in multiple steps, and they stagger them so you can execute more things in parallel. So the obvious caveat to that, if the next instruction depends on the result of the previous one, then you don't know what the next instruction is going to be. So what the processor is doing is it's going to guess. It's just like, oh, you have a jump instruction, and maybe it's a virtual call or a loop or an if statement. I'm just going to pick one, start executing this one. If I'm right, I'm going fast. If I'm wrong, it's no worth than waiting for the instruction to be finished. I just discard what I prepared, and I start over, and I'm good. But every time this happens, what the processor has to wait, and the pipeline is between a few operations to a few dozen steps, and therefore it will have to wait that many cycles, right? So potentially it creates big bubbles of having to wait. So the advantage of vectorization is if you execute column-wise, let's say instead of you have an expression which is A minus B plus C. If instead of doing each expression on the whole row every time, right, which potentially has a lot of virtual calls because you have expressions that are implemented using a polymorphism of expressions or things like that. Instead, you do column-wise, one column at a time or two columns at a time. You do all the A minus B first. You take the result, and you do that plus C, right? So simpler expression. You have tight loops that do one thing many times and are going to be a lot more efficient because they are very easy to predict. The branch predictor just does the same instruction again and again, and it's only wrong when you exit the loop, which is negligible overall, right? And then the modern processors also have SIMD instruction, single instruction, multiple data, that can evaluate the same instruction on multiple data at the same time, right? So this, if the width of this instruction is 4 values, for example, you actually go 4 times as fast, right? And this is the advantage of doing loops that do one thing many times, and it goes much faster on the processor because of that. So even though logically we're doing the same number of operations, it goes a lot faster because we take better advantage. The other thing we take advantage of is the cache on the CPU. So the other thing that's slow is fetching data from the main memory. It takes about 100 times as long to fetch data to main memory than to execute an instruction. So whenever the CPU does that, it has to wait for a long time. And so because when you organize the data in columns, everything we're going to work more locally on, we're going to fetch exactly the data we need, right? Because we're not looking at value across rows that are more scattered in memory. We picked tightly packed columns to work on them. We have much better cache locality, and it also takes more advantage of that, and we have a lot less time waiting on things. The other thing you need is this efficient data exchange that enables vectorization, so a format that is column-oriented and is going to be very cheap to send over the network between threads, and a columnar store that's going to enable you to collect data faster from disk, right? So if we think of those tables as two-dimensional things, right? In your head, the table has rows and columns. On disk or in memory, it's all one dimension, right? You have to put all the bytes after another. And therefore, you have to pick if you're going row-wise or column-wise, right? And if row-wise is more efficient for OLTP type, for OLAP, it's better to use column layout because most of the time you query a subset of the columns. And it's going to be a lot faster to fetch from disk one column at a time or take the whole column at once rather than doing a lot of little jumps. And it's also going to encode, it's going to be much better to encode together data that is of the same type. And if the data is sorted or other things, you can take a lot of techniques that are going to be faster than brute force compression on, say, doing delta encodings on values that are sorted, or doing dictionary encodings and things like that, or run length encoding, and making things a lot faster by having space-efficient encodings that are also much faster. So if I go back to this diagram, I'm like, okay, so we had 3 easy steps. And now we do parse the query. There's a whole ton of things we had to implement that are fairly complicated. And now we're done, right? No, the thing is, building query engine, you're never done. There's always more optimization. There's always things. It's never, literally never done. And if you remember the Stinger initiative from Hortonworks, where they laid out all this work to make Hive faster, and it was great. And what happened over those 10 years? Well, over those 10 years, things have changed, right? The ecosystem has evolved. And well, like when the ecosystem and the technical constraint change, well, the solutions have to change, right? You don't do things the same way. So if you go back a little bit to what were those limitations of Hadoop, right? We had this immutable data, no transaction. We were tying compute and storage, right? Because we're moving compute to storage. So we kind of, the CPUs that are on the same machine as the disk that stores the data have to execute things. So it's kind of creating a lot of constraints on how you optimize and scale up and down the workloads. And it's reliant on those discrete steps persisted on disk, right? Like, if you remember this MapReduce image, like the first reducer can only start after the last mapper is finished, right? So you have this big synchronization step where the slowest mapper is going to slow down this whole operation, and then you have the same thing for the reducer. And then if you're chaining together multiple MapReduce jobs, you're doing that over and over, right? So introducing a lot of latency. Right, data is immutable is genius, right? Because replication and consistency of data is a lot easier if you cannot modify it, right? It's great. And you don't need transaction where data is immutable, right? Turns out, I don't know, who knew in the room, right? Like transactions are useful. Oh, I see, oh, thank you. I see some others. You know who else knew? This guy. Not only he knew, he told us hammering on the head, what are you guys doing? So yes, thank you. And then there's kind of, maybe you should be paying attention and think about this, right? So the other aspect is we're coupling storage and compute, right? Like back when I was at Twitter, there was the person in charge of the Hadoop cluster. Like, okay, like we're designing the next iteration of the Hadoop cluster, right? And we're going to amortize it over 5 years. And we need to order the machines, so putting it in the data centers. You need to tell me what's the ratio of compute to memory, to disk you need, right? Like for the next 5 years. Are you workload CPU bound? Are they IO bound? How did you tell me? I was like, I don't know, and it's going to be different in 6 months. We can look at what we're doing now, but what is going to be, I don't know. And so we ended up always having to deal with whatever we got, right? Like, oh, so maybe we don't have enough storage, so we'll need to either delete more data, or we'll have to add more machines, and then we're not using the CPUs, there's a lot of waste. Or we don't have enough CPUs, so we kind of add more machines. Now we're wasting all the disks. And invariably, it ends up with, I don't know, we're just going to have to reduce the number of jobs that need IO or reduce the number of jobs that need CPU and figure out other ways to do this, right? And by the way, this is not a Hadoop problem, right? This is building a cluster with storage and compute together. So Michael Stonebreaker also pioneered Vertica, which is one of the first commercial massively parallel databases. It had the exact same problem, right? Like, so you design this cluster, you have like better SQL-oriented interactive queries, but if you have many teams that want to use it, they end up competing for those resources, and it's not elastic, and you cannot. It's very contentious resource. So while all this is happening, meanwhile, like things have changed. So the key things that change a lot how we build things today is the networks, they went faster, they became faster than the disk did, right? So that changed the ratio of how long it takes to access data through the network versus accessing it locally directly from the disk. Which means, actually, we didn't need to move the compute to storage anymore. And that's a huge, huge change. The other thing that happened, like we think about Moore's law of a single thread becoming much faster over the years, it becomes less true, right? Like the curve has been like slowly flattening. So what that means is when designing processors, if we want to keep designing these processors that do more stuff, they ended up being more parallel, right? Having more cores. And the machine had more cores, more memory, more disk, more parallelism. And you can see it today, right? If you think of like DuckDB, for example, has a much, much different design from Hive or Trino or Presto of all those other engines that start from something like, oh, we're going to scale across many machines, right? Like because now the ratio, of course, sharing data in the same machine is not the same as sharing across machines, right? When you're sharing in the same machines, maybe you don't need to copy the data anymore. I don't know, like ask the people we know. The other thing that's changed is the cloud has become ubiquitous, right? So remember we had to figure out, oh, someone is going to rack all those machines in our data center, and then we're going to have to figure out how to make good use of them because they're going to sit there and we paid money for them. And so they cost us money whether we use them or not. Now, everything is elastic, right? Like if you think like the marketing team needs to run these big jobs or like we need to migrate this whole data set, it's going to take a big chunk of resource and next week we don't need it anymore. Well, easy, right? You just spin up a cluster, do your thing, even for a few hours, and then you're done and you pay only for what you use. The other big things is, remember we don't need to move compute to storage. Now that means that we created this new decoupled storage, like services like S3 and GCS and all the bucket stores that exist. And so it's fast, it's cheap, it's decoupled from compute, right? It's even cheaper if you don't use the data, right? Like you don't need to know you're going to need the data to store it because you can get rid of all the expensive compute that was tied to it and just store it. And even, there's tiers that you can move data to things that you don't have to worry about it anymore and you can decide later if you're going to use it. So the old school, we were tying compute and storage together and moving the compute to the resources that had access to the storage in a fast manner. We're like putting a lot of constraints on scheduling and resource allocation. New schools is a different set of nodes that access this abstracted out storage. And so you can even take down all the compute nodes, right? Like we don't need them at the moment. We don't need any compute nodes anymore. It's just stored. And if suddenly someone needs a lot of resource, like have a spiky big thing to do for a short amount of time, we can provision more nodes temporarily and then release them and everything's easier. And so following that, we saw the emergence of the cloud-first data warehouses. I think people have mentioned in other talks Snowflake and BigQuery, and they were great, right? If I remember, I used to have this cluster, and I could do SQL on it, and it was like hard to share those resources. And now I pay-per-use, it grows on demand, there are very little resource contentions, it's great. However, for some reason, they use a proprietary storage format, right? The data is only accessible from within. You have import-export costs, where it's pretty expensive to get data in or out. And it creates new silos, right? Because people use specialized tools for different things they're doing. Right, like so, typical workflow, you have a team that does ETL, gets data from a bunch of things, maybe it's staged in your blob storage in files, and then it gets loaded into your warehouse. And then, typical workflow, it goes one way, and then we do dashboards, build dashboards out of this, and then we're done, right? except shortly you will have someone we need. Actually, you know what? We do these other things based on our data lake. And so we need to extract this data that is produced by the analyst or the data scientist and get it back in the other side. And then before you know it, you have dependencies that go everywhere with dubiously synchronous jobs that kind of get data one way or the other. It's not clear, it's very opaque. We don't know how data gets in and out, who's responsible for updating things, and it's a big mess, right? And we created silos, and it's hard to collaborate, and there's always this constraint of it's actually costly to transfer the data. And it creates these new constraints of, oh, does this data, should this data be here? How we depend on each other, and it's a big mess. And in the end, wait a minute, it's all blob storage, right? We had this great decoupling of compute and storage, and we have silos, but it's all stored in blob storage in buckets. There's something wrong, right? Like it should be an easier way to share that data. So the last part, I'm going to talk about this notion of how do we move towards composable data systems, right? And avoiding those silos. You know, we've been thinking of those databases as like vertically integrated, highly efficient. The front end knows exactly how to optimize things, how to access data, how to store data in a way that's going to be efficient for querying. And we have very integrated systems that are very performant, but that creates those constraints when you want to use different ones for different tasks that have different specialization needs. So let's say you want, okay, so first, why do you want to build your own database, right? And actually, I'm not advocating building your own database, but it's kind of how we customize things. You need to think about, okay, what are we trying to achieve? Let's say you worked at a company that has very big time series, right? It's collecting a lot of data, and maybe there's a storage that optimized for storing metrics, like it's kind of a giant cube. And you have constraints of the low latency of getting it ingested so that it can be queried, and it can need to scale up to like exabyte scale or something. So some of the questions you have to ask is, does it fit on one machine? Does it fit in memory or on disk or something? Like, you know, maybe you use DuckDB, maybe you use something that needs to be distributed. What's the latency, right? Do you accept bulk ingest, like data can show up in bulk every hour, or you have like a sub-second constraint on how fast you need to be able to query the data after it's produced. And you know, there are other techniques. If you don't need exact precisions, which in lots of cases you don't, maybe you can use approximate data structures like hyperlog or count mistakes or sampling to access data. So this is my diagram of this deconstructed database, right? Like how do we rebuild that database from components, right? So it's not building everything from scratch, but there's a lot of things that exist that we can combine and achieve like a more specialized database for a specific use case without reinventing the whole stack, which takes forever. So I split it in like 3 pieces. You have a front end that deals with how we understand queries and optimize. There's the execution engine, which is how we make the result, we materialize the result. And there's a storage layer, which is responsible for persisting the data that you're going to query. So on the first layer, I'm going to add my, governance. I know we've been talking of, how do we query things efficiently and something. The other problem, right? Remember about the spaghetti bowl of dependencies, right? You need to understand how data is transformed, how often, where it's going, where it's coming from. How do we guarantee quality? How we understand the full graph of dependencies. That's what open lineage is for. And integrates in the front end, right? You can integrate with a bunch of frameworks, Spark, SQL, all different things, to know exactly where the data came from, where it went, when it was transformed, and a bunch of other metadata that comes with it. How many rows did you produce and things like that. So if we go, remember, I'm going down the layers in that view. The next layer is calcite, right? Calcite is a database where we remove the internals or we made the internals pluggable. It's Julien, so, and when I say we, it's, is all us. This is all open source, right? So those are projects. We all have our stakeholders in them, right? We can all contribute and be part of them. So obviously, I didn't write all that code. So you have calcite. All the internals are pluggable. So you get an optimizer. You get the understanding of SQL and the relational algebra and all of this. And it's a database with bring your own internals. It's used in many projects. It was used to make Hive faster. And it's become like a key project. Second one, we need a standard plan representation, especially if we're going to do decouple different storage layers from an execution layer, right? If you need to have to federate different things and take advantage of the capacities of doing filters or aggregation, let's say you have a system which is a specialized storage layer for time series with metrics in them that knows how to do aggregations really well. The advantage of using Substrate, which is a more emergent project to represent plans, it makes easier to reason about pushing down some of those operations to other systems, right? Like you have the kind of federated query engine at the top, understanding how you're going to push filters, expressions to lower layers, and have a common understanding of this, right? It facilitates transpiling, language independence. You might use SQL, might use data frames, but it all turns into plans that can be optimized and can be passed around. Next one is, so we talked about vectorization and needing a representation of data in a columnar fashion. Arrow provide that. It's in-memory columnar representation that's optimized for enabling vectorization. And it's also optimized for enabling zero-copy network exchange, right? Because all the data, all the reference in Arrow are relative. The in-memory format is exactly the same as an on-wire format, right? You can just copy the buffers around, and it's the same data. And so there's zero serialization. You can point the network stack to your buffer in memory, send them on the network. On the other hand, you can take the network buffer and just read the data directly from it without any kind of transformation or copy. It's cross-language compatible, and it also enables high-quality vector kernels, compute kernels, because all those operations, all the granular operation you can do on vectors to enable vectorization can be provided and recombined in a vectorized engine on top of it. The next one is data fusion. Data fusion has become a standard of a library you can use to recombine, to take advantage of modern CPUs, right? So it implements all those understood techniques of vectorization, and you can focus, and it's very extensible. So you can focus on what makes your application special, right? You can take data fusion, not have to worry about re-implementing a whole bunch of logic, how joins work, a lot of operators. Just use it, but it's also very extensible. And so if you have things that are specific to time series, like aligning time series so that you can join them together or things like that, you can do that. And so I've been done, right? Like, so we looked at the front end, the query engine, the front end, the optimizer, the execution layer with vectorization and data interchange and so on, and going down to the storage layer. When you store, you need to expose an abstraction of a distributed data set with pushdown, right? You need to be able to do a distributed read. So there's a table and you can read it in parallel from multiple machines in an efficient way. It needs to have a format that can efficiently be turned into this vectorized enabled format, and needs to understand pushdowns, right? How do we read only the columns we need? How we don't read the partition that obviously don't fit, or subset of the data that don't match my filter. If I have limits, right, I don't read all the data, and possibly I can even push aggregations to the storage layer, right? If all I'm doing is counting rows, I don't need to read all the rows to count them, right? I just count them in the storage layer directly. So in that ecosystem, we have two different abstractions. And one is this standard open data lake with Iceberg and Parquet, which is great for bulk updated, scalable, cheap storage, right? You update data one big chunk at a time. And the advantage is you don't need to operate your service, right? It's in your blob storage. Or at least you don't need to operate any service that need high throughput, low latency access, right? You might have an Iceberg catalog on the side, but it's just keeping track of what tables exist. All the data-related operations are directly through the blob storage. The other layer can be done with Aeroflight or any kind of distributed Aero service representation. It enables a much finer grain implementation, right? So now you can decide, you can build your own low latency transactional storage if you want and expose as an Aeroflight or similar service. And it has a lot of flexibility, but it comes at a cost because you need to build your own service and that can be tricky, right? Then now when you have workloads that go up and down and you have spikes in compute, like because we decoupled storage and compute, your storage service needs to scale up and need to be able to scale up reads and things like that. So it's kind of the general idea of building your own storage in this layer. If you use Iceberg, you have this nice thing. So remember how we talked about, we have data in multiple engines and then we need to get the data in and out of those. Now in Iceberg, you own your own data. It provides a proper table abstraction. And it's based on the scalable, cheap blob storage that you don't need to worry about, right? Because if we assume the spherical cloud provider in a vacuum, you can consider your blob storage to be infinitely scalable, always available. But if it's not completely true, at least it reached a very high level of that. And the best thing is you don't have to be doing anything for this to happen, right? You can rely on it. And if the SLA gets to a point where you're happy with it, it's very rare that you have to worry about the limits of blob storage. So what I mean by a proper table abstraction, remember how we used to have this file system abstraction, right? Like we shared data as files, which created a lot of constraints, right? Like it was never very clear how you update the data. Remember how I said like we have no transactions? Even appending to a table had weird semantics, right? Or deleting some data had weird semantics. If you don't have a way to coordinate between the readers and the writer, then it makes it really hard to to be able to append things without creating phantom reads or like inconsistent reads. Or like, what if someone is reading or listing the folder while you're adding files to it? What's your logic here? So Iceberg is adding this notion of snapshot isolation, right? There's a clear definition of what the version of the dataset is, right? So you always create snapshots which have a clear list of all the files that makes the current version of this table, which means whoever is reading the table at the moment is going to read that version. You can add files you want. You don't have to worry about this. Nobody's going to read them until you atomically update what's the current version of the table. And now, whoever was reading the old version finished reading that. The next time they read, right, they're going to know what is new in between, and you have clear representation what's new, what's not new. And the other thing, so we can have consistency, atomic update, snapshot isolation. You can still read the old version while the new version is being written, and even after it's been written. And you can easily roll back because you have pointers to previous versions. So if you push bad data, well, you just roll back to the previous version of the table, tell the downstream consumers to rerun, and you're done. It has this partitioning abstraction. So before we add the same file-based abstraction in data lake, where, this folder in this partition, that folder. So we ended up coupling consumers and producers by doing incremental processing based on, I'm reading files that have this pattern, right? And every time, if they show up, then I process them. And so this now becomes all abstracted out because we have a proper table abstraction I'm reading this interval on this column, and I can think about it logically, And you can even repartition things on the fly and not impact any of your processing. And of course, it does efficient push down, projection, filters, limit, and enable fast access. So in this model, the service is your blob store. You don't have to worry about the scalability aspect. And I'm not showing the catalog again here, but all the critical paths that require high volume, high availability are on that path. The part that are hard to scale. So if we think about this open data lake, we have on one end centralized parts like the data, the catalog, the governance, the lineage, you can centralize this. And what's specialized is the compute engine. So now we're in this nice world. So I put some example, please don't tell me you're not on the slide. I know, I'm sorry. I had only 4 spots. But like examples on things that, yes, you can have your storage. Remember, it's all blob storage in the end. And you can use the best tool for the job for things. And now trying out this new, I don't know, machine learning library that needs to read all your data, this new thing, it's very easy, right? Because you don't have to have a big ETL job that are going to pull all the data from one thing and push it to something else. Okay, we own our data. You know, if one of those change their pricing model and we don't like them anymore, we can threaten to use their competitor, right? And it's kind of easy and all of that. Not that any of those companies are evil, right? Like that would not happen. And then, you know, on the compliance, governance aspect, all those things integrate with Open Lineage in some way. And you can track how data is derived across all the engines, right? It's not like vertically integrated anymore. So, as a conclusion, and I'm going to venture myself in making some prediction or suggestion, take it the way you want. Conclusion, I talk about the combination of open source and cloud services and how that enables building composable data systems, right? And then like working from this deconstructed database, we have these components and we bring them back together. On one end, in the open source, you have the formats that enable composability, right? Like because we standardize certain aspects, like plans, in-memory representation of data exchange, like on-disk representation, or like lineage for governance. Now we have all those components that are going to plug together. So this is a very important part of the ecosystems. On the other hand, we have these libraries that you can use that enable extensibility, right? That you can plug in a bunch of places. So Calcite is very pluggable. Optimizers, Data Fusion is this very pluggable expression evaluation, or like it's a kind of implement part of the plan or your entire plan, or you can make it distributed or you run in locally or different things. And in Arrow, also provide the compute kernels that enable vectorization that are used in Data Fusion, for example. On the other hand, you have the cloud services that enables, you know, it's just like, I don't even need to buy machines anymore, right, to do this, right? I can run this open source software either using this reliable storage that's pretty cheap or elastic compute that I can even shut down on demand and makes it very flexible. So if I think about the future, right, or like looking at cloud storage, one element is, can think of tables versus blobs, right? Blob storage is starting to be table aware, like with the advent of Iceberg and this data lake house notion. We're starting to see as actually if the blob storage contains Iceberg and Parquet files, we are going to know how to deal with it and optimize it and do things. You start thinking like the bulk ingest versus streaming ingest, right? Like, so we see all these data lake, it's all bulk ingest. But actually you start seeing Kafka compatible implementation that are storing directly in blob storage, right? And they have, of course, they have different constraints, right? It's different trade-off in terms of availability, throughput, latency, cost. But we starting tiers that use blob storage for storing streams. Another thing to think about is this caching materialization. So of course, when you switch to blob storage from, let's say, reading directly from SSDs locally, You trade some latency, right? Like the common things is more, you take more latency in reading from a blob storage than your local SSDs or something like that. So caching, or there's this duality between caching and materialization, right? If you're caching queries or you're caching subset of the execution, it becomes close to actually materializing things, right? You can either update your view as it's going, but if you caching materialization of subset of the plans, it's kind of very similar, and the things are blending there on how to speed up execution. So if you think of this standalone caching service, right? If you have this execution engine and it can store pre-aggregation in a caching service using Arrow, or things like that, that can be a way to deal with the latency of the blob storage and making certain things more interactive or go beyond the sub-second query SLA. If we stop thinking of blob storage, but as table storage, which push down in caching, if now we know that the blobs are actually in a table format, you know how I said, oh, but if you have a flight service with Arrow, you have to handle your own service. What if we blend those two things together, right? And if the blob storage starts to be aware, look, wait a minute, this is a table. Actually, there's more things I can do, right? And let's say you send a substrate plan with filter or aggregation to it, and the service returns only what you need directly in Arrow format, you simplify certain things. So I know we had some flavor of this in the past, it didn't quite work. I don't understand why it would return JSON or things like that, but like if you think in terms of what are the actual standard formats we use in the ecosystem, that could be very powerful in really thinking about your blob storage as a table storage, optimized for this. And now if I bring those three ideas together, right, if you have this Kafka compatible service, right, that stores directly into blob storage in this raw ingest format, and you have this flight service on top, you could have an abstraction that actually knows the difference between what's just been ingested in this raw-oriented format. You can have an asynchronous thing that optimizes the storage for queries, that treats this raw-oriented format asynchronously, converts it into columns, sorts it, buckets it in the right way, in Parquet format. And then you can have an abstraction on top of this. Now my blob storage, remember how I said like it's all only bulk updates? Wait a minute. Actually, I just took down the latency to very low. And if I have an abstraction on top of it that I don't need to, even I could know that at the table level, right? Like having certain files in a certain format. We already doing compactions and things like that asynchronously to optimize storage so that we don't have to wait that much to start writing data in tables. There's a lot of things we could do. So those are just me thinking and there's a shower in the morning. They're like, oh, we could do that. But it's just ideas that things, like when you start having open standards and pluggable things like this, you can start thinking of how you reorganize those components I think would work together. And there's the collaboration between open source and cloud services.